Hello! Okay, so the challenge problem from last week's videos was the following. If c squared equals a squared plus b squared, and ab is equal to an unknown for positive values a, b, and c, then this expression is equal to this expression, which is equal to a constant r. The aim of the challenge was to solve the unknown to which ab is put equal, and write that in terms of this constant r. Now the answer is the square root of r over 2. So the particular case which we looked closely into in our previous video last week was the case r equals 1. And this is consistent with like this particular condition is consistent with the condition that was needed to obtain this particular result. That is, r being equal to 1 in this case, giving us 1 over root 2. So I'm just explaining that just so we can see exactly how that answer, that general answer, relates to this specific answer for last week's video. I also want to make clear that I did say because a, b, c are greater than 0, this implies that c minus a and c minus b are positive. That information alone is not enough to confirm that these particular factors would be positive. We require that c is greater than a and c is greater than b. That is actually given when this condition is affirmed alongside this particular condition. If a, b, c are positive, and this is true, then c is greater than a and c is also similarly greater than b. So these would be positive. I did not explicitly mention that last video, but I did want to make that clear just to neglect confusion. Okay, so I don't have a lot of space at the moment to be recording a lot, and the problem of this video is going to, unlike the last week's video of being originally devised, the problem in this week's video is quite a famous problem. So it might take a bit of time to actually explain it. So instead, given the kind of fame that it's acquired in the widespread mathematical community, I'm going to be putting a link down in the description that talks about the problem and provides some context on how the problem actually works. I'm not going to be talking about that in this video. I'm going to be talking about the mathematics behind that problem. So what is this problem? This problem is the Tower of Hanoi, and this is an example model of that, given this configuration of 9 disks. So I'll refer to these as the disks and these sticks as the poles. Okay, so those who are aware or familiar with this problem would probably also be aware and familiar with the mathematics involved behind it. That is induction. But induction, when completed, requires an inductive hypothesis. That is, you need to have an educated guess of the formula you were trying to prove in the first place. That is why it is called induction and not deduction. We will be looking at a deductive method instead, and that will be involving some functional equations. So first of all, the mathematics behind this that we'll be looking into is trying to derive the general formula regarding the Tower of Hanoi, which is the name of this puzzle. So it isn't specific just for this case of 9 disks, but for any arbitrary number of disks. Of course, it has to be positive, but we will be considering the case when there are 0 disks. Now, because we're talking about disks, that is whole items, and that means our number being assigned to represent the quantity of these disks will be discrete. So our number, let's just call it n, we'll be considering the 0 case, which I mentioned earlier, but it would also have to be part of a countable set. So that's the natural numbers over here. Okay, so now that n is well defined, we can actually, what we want to do, we can ascribe it to our number of disks. So I will be depicting this model onto the blackboard over here as follows. So these will be our disks. There are n disks in total, and these will be our poles. Now suppose that it takes m moves to move n disks to an arbitrary pole, such that this pole is distinct from the original pole. In other words, given a number of n disks, there exists a minimum number of m moves. We're saying minimum number because if there was a number that was less than m, which could be ascribed to, not ascribed, but corresponding to n, then we'll be using that number instead. So here m is the minimum number of moves required to move n disks into another pole like this. That is in accordance with the rules of the puzzle. Again, link is in the description for those who don't really know what's going on. In other words, we are looking to find a function of n which m can be put equal to. That is, m is equal to f of n, where f is our function. Okay, now let's consider n plus 1 disks, because we want to, it's just useful to compare. And it's also pretty intuitive as well. So now we have n disks and another disk as well. Then altogether we have n plus 1 disks. Now we know that if we want to move n disks, it will take n moves. But now, since we have n plus 1 disks, then we have another disk remaining. So we have to move that. And this would be to the remaining pole on the other side, which would take 1 move. But now, because we have n disks originally on this pole, given these m moves over here, then we need to actually move these to this pole over there that already has our last remaining disk. But of course, since there are n disks, that would take another m moves. Okay, so in this case, if we're considering what f of n plus 1 is, this is basically equal to the total number of minimum moves required for n plus 1 disks in order to complete the objective of the puzzle. That is m plus 1 plus m, or 2m plus 1. But m has been defined previously as f of n. So that means we have the following functional equation which can describe our the formula or relationship which we're trying to find about the Tower of Hanoi. Namely, f of n plus 1 is equal to 2 times f of n plus 1, where n is equal to 0, but it could also be equal to a natural number as well. Okay, so sorry again if I'm being a little bit too hasty about this. I just don't have a lot of time to be working with in this one video. I currently have about 9 minutes left, and we're already halfway there, so I guess we're doing okay. So what we want to do is we want to find out what f of n is. That is our objective. So let's isolate f of n by rearranging this equation. F of n is just going to give us f of n plus 1 minus 1 divided by 2. Okay, now if n is an element of the natural numbers, then n plus 1 and n plus 2 and etc. will also be an element of the natural numbers. So we can actually let n map to n plus 1. And in this case, that would allow n plus 1 to map to n plus 2. This would allow us to actually isolate f of n plus 1 instead, similarly like this. We'll have f of n plus 1 is equal to f of n plus 2 minus 1 over 2. But notice that because f of n plus 1 appears over here, then we can actually just substitute this as f of n plus 1, since this particular expression is equal to f of n plus 1, and we are particularly interested in finding what f of n is. So now that we substitute this into f of n plus 1, we will get that this is pretty much equal to f of n plus 2 minus 1 over 2. That is f of n plus 1. And now we have left to subtract 1 and divide by 2. Subtract 1 and divide by 2. So that's going to be equal to f of n plus 2 minus 1. Now we need to we can write 1 as minus 2 over 2. And then combine these two fractions together to give us this. But we can also combine these denominators together by multiplying them. 2 times 2 is equal to 4. So that's going to give us f of n plus 2 minus 1 minus 2 over 4. Now, note that this was actually the same as f of n plus 2 minus 1 over 2 minus 1 over 2. We can now substitute f of n plus 2 just like how we substituted for f of n plus 1. We can write this as f of n plus 3 minus 1 divided by 2 minus 1 divided by 2. So that is now f of n plus 2. And we're minusing 1 over 2, and now we're minusing 1 over 2 again. Okay, so that is going to be equal to, well, f of n plus 3 minus 1 over 2 minus 1. This is going to be 2 over 2, like that. Combine the fractions, that's going to give minus 2 over 2. 2 times 2 is 4. Now we're going to let 1 equal 4 over 4. Combine those fractions. Now 4 times 2 is 8. And holy crap, we actually get that we get that f of n is equal to this, which is equal to this, which is equal to this. Now the pattern here is clearly this. This is equal to f of n plus k minus 1 plus etc. plus 2 to the power of k minus 1. So etc. over here, this ellipsis, pretty much just means a series of ascending summons of powers of 2. And this entire expression will be divided by 2 to the power of k. When k equals 1, we get n plus 1, we get 2 to the power of 0 and 2 to the power of 1. When k equals 2, we get 2 to the power of 0 and 2 to the power of 1 and 2 to the power of 2. And when k equals 3, we get 2 to the power of 0, 2 to the power of 1 and 2 to the power of 2 over 2 to the power of 3. So that matches nicely with our general formula over here. Makes sense, right? Okay, so this can pretty much happen for any k we like. We just show that it was consistent with k equals 1, k equals 2, and k equals 3. But let us assume that this can actually happen for any k. And we can assume this because this is a function written in terms of n and n only. So that means if it were to be equal to this, then we could also express k in terms of n. So it allows us to assume that k can actually just be as arbitrary as n itself. Okay, so let's now put this up over here like so, and let's actually work with this. F of n plus k is 1 plus z plus 2 to the power of k minus 1 over 2 to the power of k. Okay, so is there a closed form for this particular series? Yes, there is. How much time do I have? I have 4 minutes. Whew. Let's consider this series. For any arbitrary a, that is where a is outside this interval, we'll have that this is particularly equal to a to the k minus 1 over a minus 1. Okay, you see why a has to be outside of this interval. I think it's pretty obvious, but I won't be explaining that. Basically, if we let a equal 2 so we can match these up upon comparing these series, that is okay because 2 is outside of that closed interval over there. And we want to do this because this series actually possesses a closed form. When a equals 2, this closed form is just going to be 2 to the power of k and then that minus 1. So this would be equal to 2 to the power of k minus 1, like so. Cool. Now let's distribute the negative sign across this expression. That would give us this. And distribute this fraction across the numerator. That would give us this. Negative 2 to the power of k divided by 2 to the power of k is negative 1. Okay, so now let's consider f of 0. When you have 0 disks, how many moves can you coordinate with that number of disks? 0. So f of 0 equals 0. This is the maximum and also the minimum number of moves that you could work with f of 0. So f of 0 equals 0. So now let k equal negative n. This writes k in terms of n, so k can actually vanish. But also it allows n plus k to be equal to 0. And we know f of 0 is equal to 0. So this function particularly can also vanish. And that allows us to actually finally derive a closed form for f of n without other functions appearing in this that would just make things all recursive and whatnot. So when we let k equal negative n, like so, basically f of 0 equals 0. This is f of 0, so that's just equal to 0. And 0 plus 1 is just 1. 1 over 2 to the power of negative n is just 2 to the power of n. And we have minus 1 left over. And that is pretty much what we get. F of n equals 2 to the power of n minus 1. That is, if we have n disks in our Tower of Hanoi puzzle, then the minimum number of moves to move those disks to another pole that is distinct from the pole on which the configuration of n disks